calculate for me the probability of cancer, given that I receive one positive and one negative test result. Please write your number into this box. We apply the same trick as before, where we use exact same prior of 0. Of first plus gives us the following factors, 0.9 and 0.2, but our minus gives us the probability 0.1 for a negative test result given that you have cancer, and a 0.8 for the inverse of a negative result of not having cancer. We multiply those together, we get our non-normalized probability, and if we now normalize by the sum of those two things to turn this back into a probability, we get 0.009 over the sum of those two things over here, and this is 0.0056 for the chance of having cancer and 0.9943 for the chance of being cancer-free. And this adds up approximately to 1, and therefore is a probability distribution. I want to use a few words of terminology. This again is a Bayes network of which the hidden variable C causes the still stochastic test outcomes T1 and T2. And what's really important is that we assumed not just that T1 and T2 are identically distributed. We use the same 0.9 for test 1 as we used for test 2. But we also assumed that they are conditionally independent. We assumed that if God told us whether we actually had cancer or not, if we knew with absolute certainty the value of the variable C, that knowing anything about T1 would not help us make a statement about T2. Put differently, we assumed that the probability of T2 given C and T1 is the same as the probability of T2 given C. This is called conditional independence, which is given the value of the cancer variable C. If we knew this for a fact, then T2 would be independent of T1. It's conditionally independent because the independence only holds true if we actually know C. And it comes out of this diagram over here. If you look at this diagram, if we knew the variable C over here, then C separately causes T1 and T2. So as a result, if we know C, whatever comes out over here is kind of cut off causally from what happens over here that causes these two variables to be conditionally independent. So conditional independence is a really big thing in Bayes networks. Here's a Bayes network where A causes B and C. And for a Bayes network of this structure, we know that given A, B and C are independent. That's written as B conditionally independent of C given A. So here's a question. Suppose we have conditional independence between B and C given A. Would that imply, and that's my question, that B and C are independent? So suppose we don't know A, we don't know whether we have cancer, for example. Would that mean that the test results individually are still independent of each other, even if we don't know about the cancer situation? Please answer yes or no. And the correct answer is no. Intuitively, getting a positive test result about cancer gives us information about whether we have cancer or not. So if you get a positive test result, you're going to raise the probability of having cancer relative to the prior probability. With that increased probability, we will predict that another test will with a higher likelihood give us a positive response than if we hadn't taken the previous test. It's really important to understand. So that we understand it, let me make you calculate those probabilities. So let me draw the cancer example again with two tests. Here's my cancer variable, and then there's two conditionally independent tests, T1 and T2. And as before, let me assume that the prior probability of cancer is 0.01 what I want you to compute for me is the probability of the second test to be positive if we know that the first test was positive. So write this into the following box. So for this one, we're going to apply total probability. This thing over here is the same as probability of test 2 to be positive, which I'm going to abbreviate with a +2 over here, conditioned on test 1 being positive and me having cancer, times probability of me having cancer, given test 1 was positive, plus probability of test 2 being positive, conditioned on test 1 being positive and me not having cancer, times probability of me not having cancer, given that test 1 is positive. It's the same as the theorem of total probability, but now everything is conditioned on +1. Take a moment to verify this. Now here I can plug in the numbers. We already calculated this one before, which is approximately 0.043, and this one over here is 1 minus that, which is 0.957 approximately. And this term over here now exploits conditional independence, which is, given that I know C, knowledge of the first test gives me no more information about the second test. It only gives me information if C was unknown, as was the case over here. So I can rewrite this thing over here as follows: P of +2, given that I have cancer. I can drop the +1, and the same is true over here. This is exploiting my conditional independence. I knew that P of +1 or +2 condition on C is the same as P of +2 condition on C and +1. I can now read those off my table over here, which is 0.9 times 0.043 plus 0.2, which is 1 minus 0.8 over here, times 0.957, which gives me approximately 0.231. So that says if my first test comes in positive, I expect my second test to be positive with probably 0.2301. That's an increased probability to the default probability which we calculated before, which is probability of any test to come in as positive before was the normalizer of base rule, which was 0.207. So my first test has a 20% chance of coming in positive. My second test, after seeing a positive test, has now an increased probability of about 23% of coming in positive.